יודע, חתימות כאלה, ואפילו קוראים 2.5. זה לא הכל כתבנו, יש כאילו דברים שכולנו אתם אבל אנחנו חושבים על זה. יש לנו כל עוד דברים
So, yesterday we developed the factorization for canonical ensemble. And the only method that we know how to actually use in order to solve problems where canonical ensemble representation is involved is the factorization. I remind you that the probabilities Fi are provided by 1 over z e to the power minus beta ei. Ei represent the energies at different states of the system. We have to compute the partition function z, which is a summation over I e to the power minus beta ei. And if we want to make a connection to anything thermodynamical, anything macroscopical, we have the free energy, which is minus 1 over beta, a log of z. How to solve it, how to find all of those, specifically, you see we need the partition function. In order to find the partition function, we use two assumptions. We wrote the algorithm on the board and we used two assumptions. One, the energy of the system is a sum of energies of different particles. And those particles are loosely defined, what exactly I call a particle. Okay, it's constituent. And two, the energies of the particles are independent. Independent. Okay. And the next step is the factorization, which applies whenever 1 and 2 holds. And the factorization is that z is the multiplication of I goes from 1 to n of zi, where zi is the partition function of particle number I. Okay. That's it. This is our method. This is what we're going to do. And we've already seen how it's applicable to a very simple system of where we have a two-state model. The thing is, the moment that we have this multiplication over here, everything is scalable. You shove into the system another bunch of particles. The only thing that it's affected is that we have some additional multiplicative forms over here. So everything is pretty easy, right? It's the moment that you have this. Yes?
This is for independent and non-interacting particles, but
those two assumptions have to apply.
But not necessarily the same particle.
No, they don't have to be exactly the same. This is why I have Zi. Yes. The moment that they are the same, when the particles are similar, it's just to power n. When the properties of the particles are similar.
What is it in here? N divided by?
Z to the power of n.
No, on top.
Number of
higher.
number.
Z equals.
It's
No, higher.
higher. Z partition
Higher.
function higher.
N divided by.
No, it's a not. It's a pi. The pi.
Oh.
So there is a sum
Oh, okay.
and there is a pi. Okay.
And by energy, free energy.
Okay. So this is what we this is what we achieved yesterday. We solved one example, and we are now going to another example. Okay. Yes.
One question. By energy, you mean free energy on the first assumption?
No energy of the system, not the free energy. So the total energy. It's the usual assumption in thermodynamics, right? Because the energy have to be extensive. So this is almost always hold, but you have to write it in this way. Okay. So we solved one example yesterday, and what we're going to do for the next couple of lectures is we're going to solve different examples, okay, of canonical ensemble, and we'll see that, well, the problem is usually what are those different particles and what are the different energies, because sometimes the particles can be interacting, and you have to find representation where they're not. That's it. Okay, so the goal is find a representation such that number 1 and number 2 are satisfied. Okay. And then you can achieve everything that you want by using the factorization. Okay. So we're going to the example, the polymer example. So we have a very crude, we are going to have a very crude description of a polymer. Let's assume the following thing. We have a wall. We have a wall. To the wall, we attach a molecule, which is some sort of a very long molecule, okay, which is constructed of many different monomers, right? So overall over here we have different monomers that somehow connected to each other, and they all sit and describe this very long molecule. They are somehow correlated, okay, meaning that they affect each other. Now, I've just told you that we need to assume some sort of independence, so we will throw somehow this dependence out of the window. Right. Now, the experiment, it's actually a real experiment in the lab, is that I can attach this molecule to some specific bead. Okay. This bead can be a magnetic bead, or it can have some charge on it, and I can apply external force, and I can drive this bead to the right, to the left, up and down, and by measuring how much force I have to apply and how the extension of the polymer changes, I can describe such quantities like the spring constant of the polymer or some effective energy of the polymer. Right? So this is a real experiment. You take one single molecule, it's extremely long, you connect a bead, like a DNA for example. You connect, DNA is a polymer for our purpose, more complicated a little bit. You connect the bead to it, you drag the bead to one side, and the polymer starts to extend. You can compress it a little bit. Depends on whatever happens, whatever you're doing to your bead. And you measure, for example, the elastic modulus or the spring constant for a given temperature T of the system. All right. זה מפריע לי שאתה אוכל פה. זה יהיה אחרון עכשיו. The next thing that we do, we need to model the polymer somehow. Okay? So every physical system here, it's very complicated. Why it's complicated? Because well, the different interactions between the different monomers are complicated. There are different forces, etc., etc., etc. So what do? We build a simple model that we can build and understand it, solve it, using this factorization and canonical representation. So what do? We look on the this very long molecule, and we say, all right, so let's describe each and single monomer as a line or as a vector, which with a specific direction, and our vectors or our monomers can point either up, either to the right, or to the left or to the right, up and down.
What do you call it?
Monomer. Monomer. A single molecule. Alright. Now, you describe all of this complicated creature by saying, well, I have some specific monomers that are going up and down, and they have exactly the same length. Okay? Right? And eventually, I connect them to some bead. Let's call it our mass. I can have it mg. And I have a pulley over here. Right? And by modifying the mass of this bead, I can make an extension or compress the monomer, and I measure everything at some given temperature, T. Okay. So this is a very crude description. This is a very crude description of whatever happens in nature. So instead of monomers that can be oriented in X, Y, Z, however they like, and they somehow affect each other, I have just very simple vectors. Okay. Now it's not enough just to say, oh, I have a vectors and I have a specific force that's dragging everything downside. I need to describe what are the energies of the system. Okay. So how I describe the energies of the system? I'm telling you the following. The moment that the monomer is oriented, forget the force for example. Let's look on every single monomer. The moment that the monomer is oriented in the direction of xy, its energy is going to be 0. 0 and 0. When the monomer is pointing up or pointing down, its energy is going to be absolute. Okay. Now, I assume, for the simplicity, otherwise it's going to be much harder to solve, that the energies of the different monomers do not affect each other at all. Right? That's it. So this is the setup, and I want to compute the elastic constant, the spring constant of this polymer, of my model, right, as a function of the temperature T. Right? This is the question. What is the spring constant as a function of T for this system? I neglected a lot of things. And usually in physics, this is what you do. You have a system, right? You have a system, you neglect a bunch of things because otherwise it's unsolvable. And you look on the minimal model and say, okay, how it behaves, how I solve it. What can I get out of it? Yes, questions? כן, אני אתרגם.
איך אפשר להזניח שהאנרגיות לא משפיעות אחרת? כאילו, שזה לא מושפע.
Okay. How can I neglect energy interactions? Well, I just did, right? Nothing bad happens to me. The real question is it still applicable? This is the real question. And usually this is what I do in physics. I look on the system and I make a bunch of assumptions. Usually those assumptions are such that I can solve something and not just go to a lab and measure it, or build a computer program that can solve it. Therefore, I need to do something, and if those assumptions penetrate into my system, I compute, look on the result, and compare it to whatever happens in nature. And if it somehow works out, then I said, oh, now I understand what's actually going on. What are the important quantities? So the nature of the game is there is something which is very important and it should be left inside, and there are a bunch of other things that not very much important and I can throw them out. Okay. And what we will see specifically for this general question, how the elastic modulus or how the spring constant behaves as a function of t, you don't really need all those interactions at all. Other questions? Yes.
Did you define the energies per direction, or is it like a given physical property?
So the assumption is here, when I'm pulling this in a specific direction, okay, the natural thing for any monomer to do is to align with respect to this direction. So I prefer to be in the x direction and not flip in the y direction. This is why I define it like that. Okay? This is the rationale. Yes?
I mean, I understand the pattern you are using in order to solve the question, okay? But you are using so many assumptions, so I don't understand
No,
it's valid.
It is valid.
Because even the energies, you are telling me
It is valid. It's going to be
0
valid.
or E, but here, like the diagonal is not a straight one. So you have like in between like cosine and
So what
cosine.
I'm going to describe to you that eventually the result of what is the behavior at large temperatures of my spring constant for this guy and for that guy is going to be approximately the same. Yes?
Why is the vector against the direction of pulling 0?
Oh, so you can because for the simplicity, but you can actually also modify also those guys. You will see that that doesn't really matter. Okay? Yes?
Also about the orientation, is that oriented towards like a specific place? Is it like a universal?
No, so I'm looking on a very specific, I'm saying my model is a two-dimensional, so let's assume that everything happens on a specific way. It cannot move in the z direction, which is perpendicular to the board, right? And I'm pulling it over here. And I want to solve this model. Can I continue? Okay, so what do we need to do? Remember, the algorithm is resetting the temperature. We set the temperature already. Next, let's write the energy of the system. Okay? Let's write the energy of the system. So how I'm going to write the energy of the system? So let's assume the following. The algorithm, write down the energy of the system. Write down the energy of the system. So first of all, I need to know how many monomers are pointing in the up direction or in the down direction, right? So ny plus number of monomers in the plus y direction. Ny minus number of monomers in the minus y direction. What else? We have nx plus number of monomers in the plus x direction, and nx minus number of monomers in the minus x direction. Okay. Now I need to write the energy. So what is the energy? So first of all, there is the energy of each and single monomer. They are completely not interacting, right? They're completely not interacting. So when I'm writing the total energy, E total, it equals to what? Well, I need to count only the particles that are, or monomers that are pointing up and pointing down. So I have ny plus multiplied by epsilon plus ny minus multiplied by epsilon. Is it the whole energy? Is it the whole energy of the system? Now it's connected to this guy over here, right? It's connected to this guy. So, well, I'm going to say there is additional energy, which is a gravitational energy, which is Lx. What is my Lx? I'll call the total length, the total extension of my polymer, model polymer in the x direction. I call it as Lx multiplied by mg, and let's put it here another constant, u0. Why? Well, because it depends on the level from which I'm measuring what is the gravitational potential energy. It's always undefined, right? There is always some constant that appears over there, and I'm choosing this u0, and I don't really care what this constant is, because it's a constant, so I can choose this as 0. You'll see later that it has absolutely no effect if it's 0 or not. Okay? So this is my energy, total energy. Remember, the algorithm works the moment that I somehow write down the whole energy as a sum of different particles, or energies of different particles. Now, this does not look exactly as energy of different particles. Well, let's just write down what is Lx. So Lx, it is nx plus minus nx minus multiplied by A. And A is the size of each single monomer. That's it. The moment we started to write, we have this energy. The next thing is somehow to write it down as a sum. So let's go and do whatever we need to do in order to write the energy as a sum of independent energies. Currently, the total, it is nx epsilon, ny plus epsilon plus ny minus epsilon minus nx minus, I'm sorry, this is plus,
Yes.
this is plus, nx plus multiplied by mg, okay? And we have plus nx minus multiplied by mg. So this is our total energy.
A.
Sorry? What? A. MGA. Now I don't really like this MGA, so I'm just going to say mg is just the force that I'm pulling down. So mg equals to some tau. This is the force with which I'm pulling down on the pulley. Okay. Well, this is cumbersome because it's not exactly some different stuff, yes, at the first glance. But I can say, well, let's do it the following. I want to write over the whole thing as a summation. Don't like this marker. A summation of I go 1 from n, from 1 to n, ei, where ei, in our case, or let's call it epsilon tilde I, where epsilon tilde I, effective energy of particle number I. So look on this system. I'm actually, what I'm doing, I'm going over each and single particle, and according to whatever is written over here, you see each particle have to be in one of the 4 states. Either it's up, either it's down, either it's to the right, down, or to the left. Okay? One of the 4 states. So it's going to contribute one of those 4 states either to ny plus, either to ny minus, either to the nx plus, or to the nx minus. Okay? So I'm going over each and single particle, and it's either contributes over here, or over there, or over here, or over there. So although I defined the original energies as epsilon, epsilon, 0, 0, now I'm saying, okay, so let's look on the contributions to ny plus. If my particle is pointing up, so the energetic contribution is in this term. So the energy, the effective energy, is just epsilon. Great. We are going to the next. If my particle is pointing down, it's contributing only to this term. Okay. Only to this term. And the energy contribution of all the particles that are pointing down is ny minus epsilon. So each particle contributes epsilon. We're going to the next term, this guy. So those are the particles that are pointing to the right, right? So all the particles that are pointing to the right contribute minus nx plus mga. So instead of mga, we write tau. So each and single particle contributes minus tau a. Great. Now, the last term, this guy. So all the particles that are pointing to the left contribute to this term. How many of them? Nx minus. How each of them contributes? Mga, which is tau a. Okay, so this is epsilon I tilde. Not the original energies where we have only epsilon, epsilon, 0, and 0. Okay, we created new particles, right? The new particles came from, or the additional energies for each and single particles came from where? They came from the pulley, right? That's it. So the particles were independent, they still independent, but the energies are different. Those are not the original energies of the particles, they are effective energies. So this is some sort of an effective energy representation of the original problem. Okay, so we wrote the energy as a sum of energies of different particles, right? And we also know that all the different particles, or all those different energies, are completely independent of each other. So that's it. The moment that I have this, I know that z equals to z1 to the power n, right? Because all the properties, energetic properties, are exactly the same. So I need only to compute z1. What is z1? z1, it is e to the power minus beta. We go to this state, epsilon, plus e to the power minus beta. We go to this state, minus tau a, plus e to the power minus beta epsilon, plus e to the minus beta tau a. That's it. So this is our z1. If you want to write it a little bit differently, you can. It's simply 2 to the power e to the minus beta epsilon plus 2 hyperbolic cosine of e to the power, I'm sorry, beta tau a. So what do we obtain? We obtain that z equals to 2e minus beta epsilon plus 2 hyperbolic cosine beta tau a, all this to the power n. The free energy is minus 1 over beta log of z1 to the power n, which is minus 1 over beta. We have n over here, and it is a log of 2 e to the power minus beta epsilon plus 2 hyperbolic cosine beta tau a. This is the free energy. You want to compute the energy now. It's very simple. The original question, though, was not what is the free energy. It was not what is the energy. It was what is the elastic constant. Right? So we assume that this monomer behaves as if it is a spring, and I want to study a little bit the behavior of this spring. So in order to find out the behavior of the spring, I don't need the energy, I need something else. And this something else is the total extension of the particle, right? So how I measure elastic constant, I'm saying, well, F equals to minus K L minus L0, something like that, right? So this is the Hooke's law. I look on all of this, I apply a little bit more force, I get a little bit more extension. Okay? So the proportionality over here between the applied force and L minus L0, or the extension of the particle, okay? This is the elastic modulus. So in order to compute this, we need to find the total length of our polymer, right? So the total length of our polymer, it's a random number, right? We look on this, the polymer always oscillates, right? So we have this. Great. Let's make this. So this is the wall, and this is the pulley. And I'm pulling on this, but there is a temperature. So all of this fluctuates all the time. So the extension is always modified, maybe not modified by a lot, but it fluctuates as a function of time because of the thermal fluctuations. So it's actually doing something like this, right? So when I'm saying what is the length of the polymer, it depends, because if you measure now, it's going to be one number. You measure a minute later, it's going to be something else, right? So when we're saying what is the extension, we mean what is the average extension L of x. Okay. What is the average extension L of x? Okay, so in order to measure this, what is L of x? L of x, I goes from 1 to n, and I measure what is the extension of each and single monomer in my model. Okay, so questions? No? Yes?
What are you averaging over?
I'm averaging over all possible realizations of the system.
States.
States are realizations. Yes. No. So what is L of x? Remember, each monomer have 4 different states. When it's pointing to the right, so this is description now not of the energy, but it's description of L of x. So in pointing to the right, it's A. When it's pointing to the left, it's minus A. When it's pointing up, it's 0. When it's pointing down, it's 0. Okay. Yes?
Can't you get the elastic modulus from the differential of the free energy?
I can, but I don't want to do this like that.
Why not?
You'll see in a second.
It's one derivation?
No.
Okay.
It's not. And I want to make a point. Okay, so we need to take an average of this guy. A summation I goes from 1 to n, L of x average. Okay. So what is the average of a sum?
Sum
Sum of the averages, right? The most important thing that you have to know from probability class. This is L of x. Right? So in order to compute the total extension, you have to compute local extensions and sum over all of them. Now, because the different particles are similar, right? So this is L of x. It's just exactly the same. It's independent of I, so it is n L of x. Okay, so this is our extension. How we compute L of x? Can I go and make some sort of a derivatives out of free energy and etc. etc. Well, maybe I can, but I don't want to, and I'll describe to you in a second why. For me, it's much more easier. This approach is much more easier, and it gives you a perspective of actually you can operate on the level of a single particle. You always can operate on the level of a single particle the moment that you have factorization. Okay. What is the average of L of x? The expectation value of L of x. It is, right? So we have 4 different states. So this is A, we have minus A, and we have 0 multiplied by something, and 0 multiplied by something. Okay. So we can write down what we multiply them by. The probability to be in the right state, the probability to be in the left state, the probability to be in up state, the probability to be in down state, and we sum up over everybody.
You said they're independent, so it's just a quarter for each.
No, it's not.
So that each
No, it's not.
Okay.
Not. Absolutely not. What is those probabilities? F right, F left, F up, F down.
E to the minus beta.
Exactly. A multiplied by e to the power. What is the energy when I'm in the right state? Minus, so it is minus beta minus tau A, right? Divided by Z1. Minus A, e to the power minus beta. The energy corresponding to pointing to the left is tau A, divided by Z1. Here I don't really care. Why?
Multiplied by 0.
It's multiplied by 0. So you see, this guy is not quartered. So what we have A multiplied by, here we have e to the power beta tau A minus e to the power minus beta tau A divided by, what was our Z1? 2 e to the power minus beta epsilon plus 2 hyperbolic cosine of what? Beta tau A. We're fine now? Okay, great. So this is just Lx. Lx large is A. Instead of this, I can write it as a 2 hyperbolic sine. And then, so 2 hyperbolic sine of beta tau A. And here I have 2 e to the power minus beta epsilon plus hyperbolic cosine beta tau A. Okay. I cancel and multiply it by n. Right? So 2 and 2 get cancelled. And this is a very nice expression. Okay. So what is the elastic modulus when I look on this guy over here? So I can take a derivative, right? I can take a derivative, but I don't really want to. Again, derivatives are ugly. We can look on this and say, in what regime we expect elastic behavior. So first of all, this is not something which is linear in tau, right? There is no linear connection between tau and L. It's an ugly connection that involves hyperbolic sines and hyperbolic cosines. So it's nothing linear here between the force, which is in our case tau, and L. Nothing linear. Okay? But, and this is not an assumption, but where elasticity works. For what forces you expect elastic response at all? So if I would try and hit the wall extremely hard, will I get an elastic response?
No.
Yes.
No, it will break, and it's definitely not elastic. Either the wall will break or my hand will break, okay? It's not an elastic response. Elastic response or what is called linear response, it's applicable only when your forces are small. Okay? So when I'm looking on this guy, I'm saying, okay, if I want to go into some Hooke's law description, I need to make the following assumption. Tau goes to 0. Right? Tau goes to 0. So for this to work, it's not enough that tau goes to 0. Right? We want that beta tau A goes to 0. Or tau A divided by k Boltzmann T goes to 0. Only in this regime, I expect some sort of linear response, some sort of a Hooke's description. Oh. So what do? We take the right-hand side and expand it, right? And expand it in the limit when tau A k divided by k Boltzmann T goes to 0. What happens to cosine, hyperbolic cosine of beta tau A when beta tau A goes to 0? To what value this guy approaches? To 1. What happens to the hyperbolic sign in this limit when beta tau A goes to 0? Beta tau A. Not 0. Beta tau A. Indeed it's 0, but 0 is never enough. 0 is nothing. We don't want nothing. We need some sort of an effect. Right? Of course there is something else. Okay? But the moment that you have something and it's not 0, it's usually you can stop in this place. Okay, so what we're getting in this regime, Lx is n A. Instead of sine beta tau A, we have simply beta tau A divided by e to the power minus beta epsilon plus 1. Okay, so this is, let's write down the temperature over here. So this is n A squared divided by k Boltzmann T, 1 plus e to the power minus beta epsilon. All of this multiplied by tau. So tau is proportional to k Boltzmann T divided by multiplied by 1 plus e to the power minus beta epsilon divided by n A squared L x. Expectation values. Okay. So this is what we've got. What is this proportionality that we have in front of Lx?
Is it k?
This is
Minus.
well, you don't need the minus, right?
This one is the k.
This is the k.
This.
This is the k, the spring constant that we'll be looking for. Because if you're extending, or if you have a specific value of Lx, how much force you have to apply in order to restrict it. Right? In order to get the particle to a very specific Lx, okay, you have to apply force which is proportional to Lx. The proportionality constant, this is your spring constant. Okay? And you're done. That's it. You don't have to take a lot of different derivatives with respect to different functions because usually you use the wrong functions on the way. Here, the only thing that you need to understand is, all right, what I want to calculate. I want to calculate the average length and get the proportionality constant between a linear expression that connects the external force and my length over here. So what do we see effectively? What happens to this K over here? Is it grows? Is it decays as a function of temperature? Grows. Do you expect it to grow or to?
Unexpected to shrink.
Right. So what was my expectation? So first of all, we're working in this limit of beta tau A goes to 0. I remind you, so this is K, this is temperature. We were working in the limit of B tau A goes to 0. Beta tau A. So the tau A divided by K Boltzmann goes to 0. So whatever we describe, it's not applicable in the limit of small temperatures. When the temperature will be extremely small, okay, compared to tau, right? So you won't get this limit at all. So whatever we were doing, we were working in this limit over here for high temperatures. High enough temperatures. What we expect, if you take a metallic spring, a simple metallic spring, okay, and you heat it up. You can do it in your home. You can do it in a lab. Okay. What will you get for a simple metallic spring? It was told us just before. So the expectation is the more hotter the spring is, okay, or the higher the temperature of the spring is, it's easier to pull, right? When it's easier to pull, the proportionality constant goes down. Right? This is what happens in a lab. In our case, and this is what happens to real polymers, to DNA, to whatever you want, right? The proportionality constant goes up. Metallic spring, polymer like spring. Why it happens? The forces are the same forces. So first of all, you go in the lab, you measure this. Although you neglected a lot of stuff, you neglected a huge amount of stuff, right? There are a lot of interactions, etc., etc. So the model is clearly oversimplified. It's clearly oversimplified. But it still produces effectively very similar results. And for our case is, the hotter the system is, the harder is to pull this damn polymer. Now why is that? Well, because the energies of a metallic spring are completely different from what we have. In our case, the hotter the system becomes, there are much more occupied states in the y direction. Right? You produce more heat into the system, you heat it up, more and more different monomers can point upwards, and instead of just extending and shrinking, you start to get something that does like this, okay? And it's harder to pull on this thing because it occupies much more different states. That's it. This is the very, 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 very simple physics that you can get out of this without involving all the fine details of the polymer. That's, and this happens to any polymer, to DNA, etc., etc. It's always like that. To membranes, this is the behavior. And what you understand is that what controls for high enough temperatures, what controls the system is not just the forces between the monomers, but some sort of an entropy, the number of states that you have, the number of accessible states that you're getting. Any question about this model? Because we are done with that. No questions? Great. We're going to another example. Another example is related to heat capacity of solids. So CV is dE to dt. Right, so it's basically you heat up the system and you measure the rate of increase of the energy of the system when you keep the volume constant. Okay. And there was a very interesting behavior that people spotted more than 100 years ago about the behavior for a bunch of different solids, very, very, very different solids, that behave, the heat capacity there behaved exactly the same. And what I mean by the same, so if you took this CV and you measure it as a function of temperature, you get two universal limits. So this curve usually looks like this. Okay. Here you divide it by the number of particles or the size of the system. Okay. So there is a universal constant, const, that you obtain for high enough temperatures, and the decay towards zero was always proportional to the temperature to the third order, to the third power. Not just one solid, not just one lab, many, many labs, many, many solids, some sort of universal behavior. When you see universal, what I mean by universal, that it's not just for whatever you measure it and that's it. Universal is that everybody sees in many different systems. That's what universality is for me. You start to think maybe there are some universal laws or general physics which is not dependent on the very specific properties of the different solids, right? Because you can have a diamond, or you can have a metal, or you can have different kind of solids, but still you will obtain very similar behavior of the heat capacity. So it's not something about the specific configuration and the interaction inside the solid, it's something general. Physicists, usually when they see, oh, I have a general behavior, there is a general physics over here. That's interesting, right?
The constant is different for each material?
Sorry?
The constant is different for each
So
material?
if you divide it by a specific n, which was dependent on the size of your material, it's always converged to exactly the same size.
In every material?
In all the materials. For high enough temperatures. Okay? And it always was proportional to T to the third. Okay? So when I'm telling that it's an old problem, it's really old because attempts were made to solve it already by Einstein. Right? So usually we see Einstein, it's the law, the relativity, etc., but no, the guy did a lot of other stuff as well. So first attempt to see what happens over here, we'll do exactly what Professor Einstein did something like 100 years ago. And the idea is very simple, like most of the ideas of Einstein. The model have to be simple. Your starting point has to be simple, otherwise you won't understand anything. Right? So if you look on the solid, okay, you look on the solid, and you think that your solid is some sort of a lattice, and those lattice sitting different particles. Okay. Those different particles don't care about each other. Why? Again, why not? And they can oscillate. They can oscillate in the x direction, they can oscillate in the y direction, and they can also oscillate in the z direction. Okay. So Einstein says, I have a system of n particles, total of n particles, and each particle describes three harmonic oscillators. So if to simplify, you will simplify to the bare bones. Right? So you said, I have particles, the particles are not interacting. It's solid, so they're sitting somewhere. Okay? they're sitting, but they're, well, they have to move a little bit. They have to oscillate because those fluctuations of the particles inside the solid, this is the temperature. So they have to oscillate. How I describe those oscillations? Let's assume that what? Each degree of motion of each single particle is a harmonic oscillator. So in total, in Einstein model, 3 N harmonic oscillators. That's what we have. 3 N harmonic oscillators. Moreover, another simplification, all those harmonic oscillators are identical. This is all oscillators are identical. This is the Einstein model, and you're not asking why Einstein assumed this, right? Because this is Einstein, so he can, and I can't. But actually, this is the simplest assumptions. Einstein model for solids. Okay. Now, Einstein already had those ideas, right? That energies can be quantized. Okay. And we now understand, if you studied quantum mechanics, you now know that the energies of harmonic oscillators, right, are quantized. So if you look for each harmonic oscillator, we know the different energies Ni are what? N multiplied by H n plus 1/2 multiplied by H bar W. Okay. So we know now that this is the case. Now Einstein hated quantum mechanics, as is known, but he had those ideas. He actually, the guy that started the quantum mechanics ideas, had already those ideas that energy can be quantized. So when he looked on this, well, I use exactly the same ideas that I already got the Nobel Prize for, right? Is that if the energy of the light is quantized, so the energies of those oscillators is also quantized. Now, when we look on the energies, right?
Just phonon?
Wait. We still don't know what phonon is. So the energy N bar W plus something, right? H bar W. I don't really care about this something, at least for our model. Well, Einstein had exactly the same idea. So this guy you don't care about. Why? Because it's a constant. So if all the oscillators are the same, W is the same for all oscillators. Okay. So then you have an additional constant that's exactly the same for all different oscillators inside your system, and you don't care about additional constants when you're talking about energy. Now the question, why Einstein did it? Yes?
Where did Einstein bring the formula for the energy?
This guy? So you're familiar with his paper on, what's the effect called? Photoelectric effect, right? Where did he bring the quantized energies there? Out of his big head, okay? This is an idea that explained experiments, okay? And now, there was a problem with the photoelectric effect. The explanation that brought by Einstein, and he built his theory on ideas of Fokker, of ideas of Planck, and he said, let's apply exactly the same formalism for those solids over here. That's it. There's a problem with ultraviolet divergency, etc., etc. So there is a problem if you use regular oscillators. That doesn't work. It doesn't work for photoelectric effect. It doesn't work for ultraviolet catastrophe. Usual description of classical oscillators does not work. There is a lot of divergences over there. In order to kill those divergences, Fokker said, well, let's kill them by producing a specific function. And Einstein said, well, this function comes from the idea that the energies are discrete. So this is a mathematical concept that built on in a couple of generations. And then said, well, why won't we apply it to something else? Okay. That's the idea. So you have to understand, we now look on the theory when we know a lot of stuff about our world, we know a lot of stuff about quantum mechanics. They had no idea about quantum mechanics, but they had experimental facts in front of them. And in order to describe those experimental facts, you have to massage your understanding of the outside world. And this is what they did. And eventually, after you throw out a lot of garbage, you say, well, this is most important in order to describe something. Okay, so why Einstein did all of this? You remember there are two rules for computing anything in statistical physics using canonical ensemble and grand canonical ensemble. Those are two rules. Is you have to write your energy as a sum of energies of different particles, and those different particles, or the energies of those different particles, have to be independent. Right? The moment that you have those two rules, you can factorize and you can solve something. So I haven't spoke to Einstein, right? But I suspect that this is why he did all of those assumptions. Because this is the simplest setting that you can have, without killing everything, the simplest setting that you can have in order to solve something, right? You need independence. Yes, all the particles are completely independent. Okay? The energies of the different particles are also independent. Great. You can write down the energies. Let's pick up something pretty simple, which is just n multiplied by constant. You had no idea about this h bar omega, probably. And let's work out. Right? The model is very simple when you try to solve it, because usually you have to work hard for the independence, right? But the energy over here is what? You just sum up over all degrees of freedom in your system. So E total equals to I goes from 1 to 3n of what? Of E, let's call it I, EI. And what is EI? EI, the energy of degree of harmonic oscillator, number I. That's it. So you have additivity, you have independence by construction, you basically pushed it inside, everything is independent. Okay. Now go on and solve something. Now the moment that you have this additivity, you just say the partition function is the partition function, let's call, take one single degree of freedom and take it to the power of n. That's it. What is Z1? Z1, it is a summation of n goes from 0 to infinity, e to the power minus beta n h bar omega. That's it. So what is this? It is a sum, n goes from 0 to infinity, e to the power minus beta h bar omega to the power n. It is a geometrical sum. Okay, it converges because h bar is positive, omega is positive, beta is positive, so it is e to some negative number. It's always smaller than 1. It's a convergent geometric series. It is 1 over 1 minus e to the power minus beta h bar omega. Right? Minus or plus?
I think
Minus? Okay. Yes?
Isn't the total supposed to be to the power of 3n?
Sorry? 3n, you're completely right. 3n. Yes. So,
May I ask question.
Sure.
Usually harmonic oscillators, the energy is determined by the length. of the
Okay.
harmonic oscillator. Here, that's not the case. It's determined
By something, by a crude assumption of Professor Einstein. Well, but think about it. If I would give you an harmonic oscillator, okay, and in quantum mechanics, those are the energetic states. That's it.
these are the possible states.
No, those are the only states.
Yeah.
So you solve it, right? So you're now studying quantum mechanics too.
Yeah.
All right. So if probably you solve those, and so if in an exam you write something else for a harmonic oscillator, I don't know what the grade you're going to get. These are the only energies of a harmonic oscillator, quantum harmonic oscillator. There's nothing else.
When Einstein derived this,
He wrote it. He haven't derived it. He wrote it. It's a very big difference. He just wrote it. Okay.
He did not think what n is like. It's not length or something. It's just.
In photoelectric effect, right? You study the photoelectric effect. He just plugged something inside. Why? Because it worked. The answer is because it worked. The answer over here is exactly the same. It will work. It just worked. So those are the ideas of photoelectric effects. You look on the photoelectric effect, you look on this current, and etc., and you say, oh, and if you look on the ultraviolet catastrophe, right? So over the whole realm, you have to assume something in order to describe whatever happens in reality. And this something is discretization of different states, different energies. You cannot run away out of it. It's there. If you use simple classical mechanics, there are catastrophes, the description is not right, etc. So there are problems. People have known those problems since the end of the 19th century. It's nothing new. People know that classical mechanics had a lot of problems. It had problems with respect to relativity. It had problems with respect to the molecular nature of the world. Huge problems. Okay? So, two solutions. One is relativity, the other one is quantum mechanics. People haven't known what quantum mechanics is, but they still can assume whatever the energies are. All right? So, go to Einstein. Leave me alone. Now, what do? So, we write down the free energy, which is minus 1 over beta log of 1 over 1 minus e to the power minus beta h bar omega to the power of n.
3n.
3n, thank you. Right. And we also can look on the average energy of this system, which is minus d to d beta of the log of 1 over 1 minus e to the power minus beta h bar omega to the power of 3n. So I don't really care about the free energy, I want to look on the energy. Why? Because I remind you, the question was CD equals d to dt of E. So since I need to compute this, I have to compute that. Okay. Okay, so first of all, let's compute the energy, and afterwards take another derivative with respect to temperature to compute the heat capacity. A lot of derivatives from now on. Right, so what is this? So E equals to minus 3n outside, and we have a log, or let's call it plus d to the beta of a log of 1 minus e to the power minus beta h bar omega. Derivative of the log is 1 over, so we have 3n 1 over e to the power minus beta h bar omega, and we take the inner derivative, which is minus e to the power minus beta h bar omega, multiply this derivative with respect to beta, It's multiplied by minus h bar omega. Okay. So what we obtain is that the energy equals to 3n h bar omega divided by E1 minus e to the power minus beta. Well, you know what? To do better, you can do, you can push whatever is here to the denominator, and we'll have e to the power beta h bar omega minus 1. No? Nice enough? No. No? I'm sorry. It's going to be uglier from now on. Okay. Next step, we have E, and now we have to find the derivative of CE. So CV equals dE to dt. I don't write what to take the derivative with respect to dt, so I will take the derivative with respect to beta and multiply it by derivative of beta with respect to dt. Okay. d beta to dt, it is d1 over k Boltzmann t with respect to dt equals to minus 1 over k Boltzmann t squared. This is the derivative of d beta. Sorry? I multiply by k Boltzmann? Where? No? Why? Fine? Thanks. Okay. So now we take the derivative of E with respect to beta. So what we have, it is 3n h bar omega. This stays exactly the same. And here I have the derivative of this guy, which is e to the power beta h bar omega minus 1 power 2. I have a minus because it's 1 over something, so it's minus 1. And the inner derivative of this guy, it is e to the power beta h bar omega multiplied, the derivative with respect to beta, multiplied by h bar omega. Hopefully I'm right. Okay. So CV equals to, we multiply this guy by that guy. Well, at least we have a minus sign over here. We have a minus sign over here, so at least the minus sign cancels out. So, wait, let's write it. You wanted to write it like minus k beta beta. This is what you wanted? Yes, beta squared. Yep. Okay. All right. Now, so let's look on this. So we have 3n h bar omega squared e to the power beta h bar omega divided by e to the power beta h bar omega minus 1 squared. And have we forgot something? K Boltzmann beta squared. Alright, this is the general expression. It's ugly. Not very ugly, but pretty ugly. Pretty ugly. Okay. We need to explore this expression into two limits because, well, I can push it into Wolfram or Mathematica and plot it, but usually the physics appears in some specific limits. So we need to look on the limit when t goes to 0 and the limit when t goes to infinity. So if you're looking on this as a function of beta, beta goes to 0 and beta goes to infinity. Okay, those are the two limits. And let's see what happens. Okay, so first of all, t goes to 0. Okay, t goes to 0. What do we have? When t goes to 0, beta goes to infinity. Right? So we have an exponent of beta h bar omega, h bar positive, as far as we know, omega positive, beta goes to infinity. Infinity. Okay, so it's not that I can write it any simpler than the exponent. Okay, so the exponents stay the same. But what's important, if I have a minus 1 here, I don't care about the minus 1. So it's just e to the power beta h bar omega. Right? Great. So we push everything inside. We push everything inside. So what we have, CV equals to 3 n k Boltzmann. And what is left? So we have h bar omega squared divided by e to the power 2 beta h bar omega, e to the power beta h bar omega, and we also have k Boltzmann beta squared.
No, you already wrote the tables one.
I already wrote the k.
Yes.
Thanks. Okay. So all of this is CV equals to 3 n k Boltzmann. And we can write this down as h bar omega squared. Let's write it down with t now because we will need the t goes to 0 limit. So it is divided by k Boltzmann t squared. And we have e to the power minus h bar omega divided by k Boltzmann t. Okay. So first of all, does it goes to 0?
Yes.
So yes, it goes to 0. Although we have 1 over t squared, and it explodes as t goes to 0, but you have an exponent here, and this exponent controls everything because you have 1 over t in the exponent. And it's minus 1 over t, so the exponent converges to 0 much faster than 1 over t squared explodes. So all of this goes to 0. Okay, which is nice. That's also what they observed in the lab.
Because then it was cubic.
Exactly. So the problem here, that's the main contribution, comes from this guy, not 1 over t. It comes from minus h bar omega divided by k Boltzmann t. So it indeed converges to 0, but the exact mathematical form is wrong. So something fishy. Great. So let's check the other limit. What happens in the other limit? T goes to infinity, beta goes to 0. Again, we look on this guy over here. So now we can do something with this e beta h bar omega. E beta h bar omega goes as 1, right?
1 plus beta h.
Exactly. So 1 is not enough. Why 1 is not enough? 1 is not enough because if I just plug 1 over here, I have 1 over 1 minus 1, so I have 1 over 0 squared. Doesn't care if it's squared or not. 1 over 0 is infinity. I don't like it. So I put here plus beta h bar omega. It's a little bit of a dance with the equations, what to which order to expand. 0, it's not good. No matter what you do, you don't have to. You cannot obtain 0. So this is why I cannot just expand to 1, but it's in the denominator. In the denominator, we're going to use just the 1 over here. Right? So what I'm doing is I'm replacing e to the power beta h bar omega here by 1, and I'm replacing e to the power beta h bar omega by 1 minus plus beta h bar omega. Okay. So we're getting the following result. CV equals to 3 n k Boltzmann. Here we have h bar omega squared multiplied by 1 k Boltzmann. Okay. Thanks. Beta squared. Here I have 1 plus beta h bar omega minus 1 squared. So I have 3 n k Boltzmann and here I have h bar squared, omega squared, beta squared, and here I have beta squared, h bar squared, omega squared. Oh, very, very, very nice. This all cancels out. Okay, this all cancels out, and it's simply 3n k Boltzmann. So let's plot the result that Professor Einstein obtained. According to the model of Einstein, when we plot CV as a function of temperature, that's specifically, let's divide it by 3n. Okay. What we obtain is it goes to 0, then it grows, and it converges to a constant, and this constant is exactly k Boltzmann. Exactly k Boltzmann. Okay. Now, the problem, so what Einstein got correctly from the experiments, this is the limit of high temperatures. For any solid, for high enough temperature, you'll get, if you know what exactly the number of degrees of freedom, so if you divide it by volume, you'll get that it converges to a constant which is exactly the k Boltzmann. Exactly the k Boltzmann. So in this limit, Einstein got it correct. In the lower limit of the small temperatures, so yes, it is converging to 0, but it's not converging to 0 as t to the third power. It has a much stronger conversion. E to the power minus h bar omega divided by k Boltzmann. So, very well, Professor Einstein for the high temperatures, really bad for the low temperatures. Okay, so it's kind of a mixed grade, right? Kind of a mixed grade. So it works, and we'll see that actually this result can be obtained due to something that's called a two-partition theorem, and it always produces this number, k Boltzmann. I'm sorry. But what happens at the low temperatures? So the theory somehow correct, okay? The theory somehow correct, but not exactly. Okay? The theory somehow correct, but not exactly. Now, where do you think that it can go wrong? So what is the most crucial part? What is the most crucial part in the system? In the setup that Einstein basically just neglected.
Oh, he assumed that interactions.
Particle interactions. Okay, what else?
He assumed that all the oscillators have the same name.
All right, very good. Yes.
The oscillators are coupled.
There's some coupling between the oscillators, also interactions. What usually happens when you freeze? So this is the regime where it's not working. It's over here, right? So what usually happens when you freeze something? Extremely, you go to the very low temperatures. It's also not exactly the oscillate. So if you look on two, if you look on two atoms, Einstein assumptions, you look on those two atoms, two particles, they do whatever they like. Okay? They somehow oscillate. Now, but if the system is extremely frozen, what do you expect two atoms to do? To do something together. Okay? They will depend on each other. Their motion is going to depend on each other. And not just two particles, there are a lot of different particles that will move in a coordinated fashion. Right? So you cannot simply neglect those interactions. Somehow those interactions are important, and when you neglect them, you get something wrong. So somehow we have to take the Einstein model and not throw out this intrinsic coordination of the motion of the different particles for low enough temperatures. Yes, questions? It's not about that. It's take two particles, freeze them, okay? Usually some sort of degree of motion, the interparticle degree of motion, it freezes and they just move together. Okay? Other questions? Yes.
In the original model, we have CV over N, the number of particles.
Yes.
Now it's divided by the number of degrees of freedom. Why
Yes.
is that?
So it's exactly the same thing. So you'll get, instead of k boson, you have 3k boson.
And the
But it
constant-
always was some number, constant number, multiplied by k boson. Yes. And we will see that this is a general result for something that's called equipartition theorem. And equipartition theorem says that each degree of freedom contributes 1/2 k boson. And we will see how it sets with this result over here. You will hear about equipartition theorem later. Other questions? Yes.
Here, we calculated the heat capacity when the volume is constant.
Yes.
How did we incorporate that into the equations?
Well, in first place, the number of particles is exactly the same, so this defines your volume, if you like. Yes. Okay. All right. So if there are no further questions, how exactly to do this? This is something that's called the Debye model, which is modifications of the Einstein model. We will do next week. Thank you all. About the quiz. The quiz is going to be next week. I'll send a message to everybody. Next week, exactly at this hour at 12. We will publish also who is sitting where, because there are going to be 2 classrooms. See you all next week. עד מיקרו כולל. מה? יהיו נוסחאות שנדרשות לפתרון הרגיל. כן. ראיתי, סליחה, אני פשוט... לא יהיה מודד, אבל זה לא יפגע בה. זה לא יכול להוריד, בציון זה לא יוריד. אני לא יודע, אני לא... מה זה כיתה קטנה? אתה מאוד צריך אותה? טוב, נראה, אולי אני אתכן לך לשאול במשרד. תשלח לי. יש. אין באתר. אם אין באתר תשלח לי אימייל, אז אני אשים שם קישור. אמור להיות קישור לספרייה עם כל המבחנים קטנים. לכל עוד זה סוליד. כל עוד זה מוצק. ברגע שזה מוצק הדבר הזה נשבר. אז הטמפרטורות מספיק לנפות, כאילו, פה זה, עכשיו, ברמה עקרונית, המצב הזה, גם בגז זה יעבוד. כי מה אכפת לך שיש לך כך וכך חלקיקים? הדבר הזה מתקבל בטמפרטורות גבוהות, לא משנה איזה משאב צבירה, אבל פה, אתה בטמפרטורות נמוכות, בטמפרטורות נמוכות אתה בדרך כלל כבר מוצק, שזה משהו בעיה, ואתה לא מפעיל איזשהו לחץ מטורף כדי שהמערכת צריכה לעבור. זה חשוב. אתה אומר, אני נמצא כל הזמן באותו פאזה, אני נמצא בפאזה המוצקה. בפאזה המוצקה אני מודד את הדברים. כן. שמה? מאוד מבעיה. אז אנחנו דיברנו על מעבר פאזה מסדר ראשון לסדר שני. אז לא, הפירון עובד רק עבור סדר ראשון. כל הנוסחה הזאת של קלאודוס בפירון נכונה רק עבור מצבי מעברי פאזה בסדר ראשון בלבד. מעברי פאזה בסדר שני זה לא עובד. אז אם אני אשאל אותך משהו לגבי הקלאודוס בפירון זה יהיה בבקשה, מעבר פאזה בסדר שני ראשון בלבד. זה תכלס. לא. איפה פה? לא, כי אתה יכול להגיד שהווליום הוא פחות או יותר פרופורציונלי ל-N, אתה יכול להגיד. נכון. אתה יכול לעשות את זה בצורה אחרת. יכול לצאת בצורה כזאת, כי זה בערך אותו דבר. כל עוד אתה תחלק את זה במה, קודם כל זה מתכנס תמיד לשבוע, ואם אתה מודד מספיק טוב, אתה תצטרך לדרגות הכי במערכת שלך, אז אתה תמיד תגיע לכלי. כן, אבל אין לי וי ואין לי כלום, אז אני אומר כזה היום, אני הולך למסע בירושלים, שאני יודע בדיוק מים, במודל. זה 3. כן. אני אראה לכם. לא, אז קודם כל, אני אסביר לך. מה שקורה זה שיש אינטראקציה בין השחקים, תמיד. הם מושכים אחד את השני, הם עושים משהו אחד לגבי השני. בטמפרטורות הגבוהות, האינטראקציה הזאת זניחה ביחס לאנרגיה הטרמית שהיא סדר גודל של אי בולצמן. עכשיו יש לך שתי תרומות אנרגטיות. תרומה אנרגטית אחת היא אנרגיה קינטית שמגיעה מהחום, זה אי בולצמן שלך, ויש לך מצד שני אנרגיית אינטראקציה. ברגע שהקי בולצמן משמעותית יותר גבוה מאנרגיית אינטראקציה, אתה יכול להשמיח את אנרגיית אינטראקציה. לא רציתי, זה כאילו לא צריך, אוקיי? אבל זה מה שקורה בפועל. בטמפרטורות נמוכות, קי בולצמן הרבה יותר נמוך, אנרגיית אינטראקציה מתחילה להשפיע, והחלקיקים משפיעים אחד בשני. אז תחשוב שיש לי חלקיק מחובר בקפיץ לחלקיק אחר. זה מה שאנחנו נפתח בסוף. אז אם אתה לא מזניח את הקפיץ, הם יעשו משהו ביחד, ינעו ביחד, ככה, אתם תרגילים שפתחתם במכניקה או באלסטי, וזה בדיוק מה שקורה. השאלה היא האם אתה יכול להזניח אנרגיית אינטראקציה, או אתה לא יכול להזניח אנרגיית אינטראקציה. במודל של איינשטיין היא מוזנחת מלכתחילה. מלכתחילה הוא זרק אותה להזניח. לא, זה יותר זכר, זה קוונטים פר אקסלנס בסטטיסטיקה. החלקיקים האלה, אנחנו נראה שאנחנו נקבל סקריבים נקרא לאלקטרונים, כמו זיינשטיין מגיע למערכת קוונטית נטו, כשיש לך יישום של האזור. חכה, נגיע, נדע.
דבר שני, איזה ראיתי במתווה שיש
הערכות חלופיות אתה יכול לבוא ולהיבחן אצלי במבחן, בעל פה, אם אתה למד מה שרוצה, לא מציע.
לא ארוך, יותר
אתה תלחץ? אין בעיה, אתה רוצה להיבחן אצלי בעל פה, סבבה. אני לא אתן לך עבודת בית. עבודת בית אני מפסיק. ברגע שיש צ'אט דבר, גאון הדור קיים צ'אט GPT, אני לא רוצה.
אין את העניין הדעה.
זה אין טעם. אתה רוצה להיבחן בעל פה במשרד, אין בעיה. אני לא בטוח שזה לטובתך. כאילו זה לא מכיר אותך מספיק טוב, אבל צריך קצת ביטחון כדי שאני אגיד. ומה זה?
אבל השאלה היא למה הוא נופל.
איך ייראה, בשיעור הזה והזה,
לא, אני אתן לך בעיה, אתה צריך לפתור לי אותה לבוא. זה לא נראה לי יותר טוב. בדיוק. אני לא חושב, תסתכל, ההערכות החלופיות האלה מבחינתי, אני לא חושב שזה, אתה רוצה, בדרך כלל יש מועד מילואימניקים. זו הערכה החלופית אמיתית. מועד מילואימניקים בדרך כלל מועד קצת מהחומר, אוקיי?
משהו קטן ומצומק. מה שאם יש לך טמפרטורה מאוד קטנה, מאוד חזק לכאילו שינויים של
יהיה מועד מילואימניקים. גם אם אתה תהיה לבד, כנראה יהיה מועד מילואימניקים, תגיע לשם.
אם יש משהו שהוא מאוד מאוד קר, את לא יכולה כל כך לבדוק אותו, יש כוחות מאוד חזקים שמחזירים אותך, אם את מנסה לבדוק.
אני לא רוצה להגיד אם אני אבדוק את זה יותר קלות, כי בסוף, אם אני לא רוצה לדבר יותר, זה עובר לסטודנטים אחרים, ואז אני מתחיל לקבל פה שזה סטנס, תן לי להצטרף, אז אני לא אומר כלום מה יהיה במועד מילואימניקים, יהיה קל, לא אומר שום דבר, אף פעם, אחרי הלחץ שלי, לא, אבל יהיה מועד מילואימניקים, תעשה מילואים באמצע הסמסטר, אתה מוזמן לבוא.
עכשיו, באזור עוד התחילה להתחפש, כן, התחילה להתחפש לזמן, ללכת לכנסת. היא אומרת חי, ואבא הבנתי שלך חזרה, אתה יכול להקפיץ אותי אליה?
It's actually done.
איפה?
Yes, because of the extension in the y direction. It can, if you have one-dimensional spring, it's usually operating only in the x direction. Here, due to this entropy or additional states in the y direction, it can do something like this, and it can become short.
כדי שאני אוכל לדבר איתו.
כן.
סבבה, טוב, היא עולה, לא מתקשרת. אוקיי, עוד 5 דקות, איפה אתה מחכה?
לא משנה מה?
אבא מתחיל כזה... איפה היא? למה היא מתקשרה?
לא.
אוקיי,
זה עובד במשחקים באופן כללי.
אז
זה?
כן. והוא לא רואה את הווידאונל, הוא מנסה וואטסאפ, הוא מנסה טלפון, הוא מתקשר אליי. אמא מנסה,
כן, כי כשאת מחממת באיזשהו שלב.
כולנו לא מתחילים לתפוס אותם,
תחשבי, יש לך חלקיקים. ויש לך איזושהי אנרגיית אינטראקציה.
הוא אומר לי...
היא חשובה כמובן, אבל יש לך איזושהי אנרגיית אינטראקציה. כל השאלה היא, כן, יש לך אנרגיה אינטראקציה, שזה אנרגיה פוטנציאלית, או אנרגיה קינטית. האנרגיה הקינטית שלך זה תמיד קיי בולצמן בי. זה אנרגיה קינטית. כמה אתה רוטט, זה הטמפרטורה שאתה רוטט, זה הקיי בולצמן בי שלך. ברגע שהאנרגיה קינטית שלך, טמפרטורה שלך גבוהה, קיי בולצמן בי גבוה, אנרגיה קינטית שלך הרבה יותר גבוהה מאנרגיית האינטראקציה, אתה לא... זה הטענה.
ואני מתחיל לדפוק
לא. עד... אני פשוט לא מגיע.
היא לא נתן מספר דירה, היא לא נתן כלום.
לא כולל קנון.
כן,
לא כולל קנון.
שלום.
לא כולל קנון. כל הטרמו עם המעבר פאזה ומשהו זה, מיקרו, סוף. בבקשה.
אני ניחשתי, היא אמרה שזה סביבות בניין 8, אז נכנסתי לבניין 8.
כן.
אז אני עובר מהראשונה מקומה...
זה מה שקיבלנו. זה במציאות מה שקורה.
עובר דלת. רואים לי כזה, לא פה. מגיע לקומה 14.
וזה תעשי עבור ממברנות. הם מודדים את זה. ממברנות, פולימרים, מה שאת לא רוצה, DNA. הקפיץ הזה עולה למעלה. למה? מאותה סיבה שאנחנו הרשינו לחלקיק לנוע.
סבבה, אני אומר כזה, יפה.
הוא יכול לאכלס עוד מצבים נוספים, וכשאת מנסה למשוך אותו, את צריכה להוציא אותו מתוך המצבים הנוספים האלה, למשוך אותו כלפי מטה, זה פשוט משפיע יותר. את צריכה להשקיע עכשיו יותר כוח. תחשבי, הוא בורח לשם, אז את צריכה גם להחזיר אותו למטה וגם למשוך אותו הצידה.
טוב, פאק, לעזאזל,
זה דבר על עלייה. ירידה, אתה רואה את זה בפועל בחומרים מנטליים, שהם בעיקרון כמעט חד-ממדיים.
כן, אולי הוא חטף אותה. אני יודע, לחוץ מאוד זה. אוקיי, עברתי על כל הבניין, סבבה? התקדמו לשם כתבה לשאול שאלות.
כן.
למה לא נתנו אנרגיה למשהו שהולך אחורה?
אתה יכול, אני לא רציתי, כי זה מסבך לי את המשמעות.
אני עשיתי את זה, עכשיו
שעה וחצי.
לכן אני לא רציתי לעשות דברים מגעילים.
אבל עשיתי את זה, לקבל מזה אותו דבר.
הוא לא מוסיף שום דבר כמעט.
אוקיי, אז אני משהו שאתה מתקשר אליי, הוא אומר את ה-L0 בקבוע קפיץ. אתה הנחת את זה בתור משהו ליניאר, כי ליניאר מובן של רק סדר ראשון.
כן.
אם אבא שלי מדבר,
אז זה איזשהו דבר שנשאר שם, מה אכפת לך מהו?
אבל זה לא באנרגיה, זה בכוח. זה כוח שווה L פחות L0, אתה יכול לעשות KN פחות K ועוד K מינוס K ועוד K, אבל אז יש לך כוח קבוע, זה כאילו משהו
מסתבר שתמר...
אז אני יכול לפתח את זה, תסתכל.
לא להגיד לזה, אז החליט להגיד לאבא,
שווה ל-L0 פלוס משהו,
אז כשאני...
אני יכול לעשות את זה?
זה מה שאני עשיתי. תמרי אצלך,
זה בדיוק מה שעשיתי.
לעצמו בראש. לא, אין אצלי תמרי, יש נועה שבאה לבקר.
F שווה KL.
כי כשה-L0 בעצם אתה דחפתי פנימה.
שוב, לא נתנו קום אבל זה מספר דירה, ולא זה.
זה עם האיום, מקבל 0, אתה מקבל כאילו, שהאיבר הזה של התאו, הוא לא
חברה שלה, שהיא קוראת לעצמה מול חברה שלה, טומי, למה היא קוראת לעצמה טומי?
זה משהו שמשנה, או שאתה יכול להעיף אותו?
אני יכול להעיף גם אותו אני יכול להעיף.
תחליטו רק את הסדר הראשון.
נכון.
נחמד, אוקיי?
וזה היה שעתיים, בראשון בערב, שאני משוכנע אני לא שואל, זה שני רוצים לשאול. על זה שעתיים בראשון בערב, אני משוכנע שחטפו את אחותי.
אפשר שאלה קטנה?
ויאללה,
עוד משפט להתחיל...
כן, אחלה משפט להיכנס היום שיחה. היא נתנה, היא הלכה לחברה שלה, בקצרה מאוד, היא הלכה לחברה שלה בלי לתת לנו פרטים לכלום. בשביל להיות גאונה, סטרנג'ר דנג'ר, לאבא של חברה שלה היא ממש קונה נוח, במקום תמרי. אז כשהגענו, חיפשנו אותה ומצאנו את הדירה, כשאנחנו תמרי, הוא אומר, לא, אין תמרי. הוא לא פרט, אז אני המשכתי.
ואנרגיה של המצב
כן.
K לחלקיק L.
זהו.
הנוצציה פה קשוחה. שאתה צריך גם מצב וגם
לא,
חלקיקים.
זה המצב וזה מספר של שוב.
ועכשיו זה עונש של החיים שלנו.
כאילו ככה אני שים
לפחות זה.
אוקיי.
אז כאילו אמרת שעבור I ו-K שהם, כאילו עבור אנרגיות שהם לא עבור אותו מצב, אז לא, פשוט ש-I, K, J ו-L לא שווים, אז כאילו האנרגיות לא תלויות.
כן, בדיוק. שזה לא אותו חלקיק, האנרגיות לא תלויות.
כן, השאלה שלי זה למה זה לא ברור עבור I ו-K שהם לא שווים, כאילו אם זה לא אותו מצב,
כי אנחנו נדבר אחר כך על נניח תיקח
כל זה, וזה רק אני, בטווח של 10 דקות, ואז אמרתי שיחות בטלפון, אבא שלי מנסה להתקשר, ואמא שלי מנסה להתקשר, ואחי מנסה להתקשר,
וזה קוונטים, ויש לך איסור של פאולי. אוקיי? שמת פה חלקיק. החלקיק השני, הוא לא יכול לדבר. החלקיק הראשון. אני לא יכול לדחוף פה עוד חלקיק. אני מסתכל על החלקיק הראשון, יש לי באפסילון אחד. החלקיק השני יכול לשבת או פה או פה.
אבל כאילו I ו-K זה מצא את המצב הכולל של המצב.
שהבכתי אותה מול חברה
איפה
שלה,
פה?
הורדתי
כן,
ככה,
אבל בסוף האנרגיות של, הטענה היא כזו, האנרגיות של כל חלקיק בלתי תלויות באנרגיות של החלקיק האחר. זה מה שאתה רוצה להסביר, זה מה שאני ניסיתי להסביר.
לא, אני מבין שזה כאילו לאותו מצב, אבל אם זה מצבים שונים, למה צריך לדרוש לי?
לא. אם אני משנה אנרגיה של חלקיק א', האם האנרגיה של חלקיק ב' יכולה להיות מה שבא לי? זאת הטענה שלי.
ובניין שלם.
תשים לב, היה לי פה EI, נניח E1, פלוס E everything else. אז עכשיו, השאלה שלי, כשאני שם פה איזשהו ערך, האם אני יכול עדיין להשאיר פה את E של everything else? אני יכול לשים פה איזה ערך שבא לי, והאם זה ישפיע על E של everything else או לא ישפיע?
לא, כאילו כשזה אותו מצב אני מבין.
גם כשזה מצבים שונים, זה לא משנה. השינויים של... האם שינויים שלו משפיעים על שינויים שלו? האם אני יכול לשים אותו, להשאיר אותו גודל קבוע ולשנות אותו או שלא? זאת השאלה. אני עובר על כל המצבים האפשריים של החלקיק מספר 1, האם זה משפיע על האנרגיה של כל שאר המצבים? זה הנקודה הקריטית. בנקודה הזאת, זה משפיע על נקודה של כל שאר המצבים. כי אם החלקיק נמצא פה, או נמצא פה, או נמצא פה, זה משפיע מה יהיה האנרגיות של החלקיקים האחרים. מסכים? אני לא יכול להשאיר אותם קבוע, אני יכול להגיד, טוב עכשיו אני הוצאתי את החלקיק הזה ושמתי אותו פה. אני לא יכול לשים אותו פה כי הם יושבים שם. או אם אני הכרחתי אותו להיות שם, החלקיק הזה כבר לא יהיה פה. אז האנרגיה של כל שאר החלקיקים פשוט תשתנה.
אוקיי, אבל אתה לא מדבר על המצב.
אני בדיוק מדבר על המצב. אני משאיר את כל זה באותו מצב, זה אותו וקטור. אוקיי? תחשוב על זה ככה, יש לי וקטור מאוד ארוך. בסדר? אני אומר, אני עכשיו עובר על כל המצבים, ואני משנה רק את הערך הראשון, אוקיי, בוקטור שלי. אני משנה. האם השינויים בערך הראשון של הוקטור משנים גם את הערכים האחרים בוקטור שלי? זאת הטענה. בסדר? אז אני משנה את המצבים, בהכרח משנה את המצבים, אבל אני מחלק את זה לכאלה דברים. אני אומר, יש פה A, ופה יש משהו. האם אני יכול להחליף את A ל-B לכל מה שבא לי, והמשהו הזה עדיין יישאר אותו דבר?
אז לצורך העניין נגיד, זה שני מצבים שונים, נכון?
כן.
וכאילו כל רכיב בוקטור זה חלקיק שונה.
כן. אני מראה לך את זה פה, שאני לא יכול לעשות את זה. נכון? אפסילון, תסתכל, אם זה אפסילון 1, אפסילון 2, אפסילון 3. מצב טוב? עכשיו, אפסילון 2, אפסילון 2, אפסילון 3. מצב טוב?
אתה אומר שהם לא יכולים לתפוס אותו.
כי הם לא יכולים. אוקיי? איסור של פאולי. אז אני לא יכול לשנות את אפסילון 1 לאפסילון 2 ולהשאיר את שאר הערכים בוקטור שלי קבועים. בסדר? בסדר? מה קורה יובל?
מה המצב?
עייף.
זהו?
רק עייף. אבל יש לי עוד הרצאה היום.
כן, זהו.
אז אחרי ההרצאה אני אהיה עוד יותר.
עוד יותר.
כן.
אתה עכשיו מתכונן מפה להרצאה הבאה?
אני עושה, מנקק טיפ-טיפה את הראש, אבל כן. מה, רצית לדבר?
לא, אני יודע שאחרי הרצאות...
אז זה או שאחרי הרצאות אם אני אהיה במצב קוגניטיבי כדי לראות אותך.
לא, תכננתי מחר.
מחר סבבה, מחר אני פה.
אבל כזה...
באיזה שעה? כן? לעדכן מה?
בבוקר כזה אני לבוא.
סבבה. אני בסמינר בין 10:30 עד 12:30.
סמינר...
סמינר של מכניקה סטטיסטית, של קומפלקס סיסטמס, יש לנו גם מחר סמינר. אז בין 10:30 ועד 12:30 אני בסמינר, ואחר כך אני לא בסמינר.
מה זה מחר?
מחר, על DNA ודברים כאלה. אם זה יעניין אותך תבוא.
10:30 עד 12:30? באיזה חדר?
עוד פעם באותו חדר. 303. 303, כן. ואחר כך אני פנוי, אז אפשר לדבר, אז אחרי 12:30.
סבבה.
מה רציתי לעדכן?
בעיקרון רשמתי את ה-QFS.
אוקיי.
עם הקירוב של כוחות קטנים.
אוקיי. אנחנו עושים גם כוחות קטנים.
כן. בעיקרון הצ'אט נתן לי 10 ציטוטים אפשריים. אני צריך לקרוא אותם.
אתה לא חייב לקרוא אותם.
לא.
אתה רוצה לקרוא את כולם? אתה לא תגמור עד זה. לקרוא אותם בקשר למה? אז בוא נתייעץ מחר. תביא לי אותם ואני אגיד לך מה בדיוק אתה צריך לקרוא ומה אתה לא צריך לקרוא. אני פוחד שאתה תתייאש בהם מלקרוא כל כך הרבה דברים.
סבבה.
אוקיי?
אז הוא הביא לי כמה ציטוטים. אני אסיים את המומנט ראשון. אם אני אספיק הערב, כאילו, רק עוד שורה ואז כזה אני אחזור למודל.
אל תכביד על עצמך.
לא, לפני הבוחן בסטטיסטית אני מתרכז בבוחן. בכללי בבחנים עכשיו.
נכון? היה אמור להיות לכם 3 בחנים. זה הזמן אותי הקטע הזה של 3 בחנים ביומיים.
לא, זה... אנחנו בדרך כלל גם בשנים קודמות, כולנו